These are not the topics that we have talked a lot. You'll see that some of the slides I created for the previous Cisco Live in 2019, I probably talked about this for 30 minutes, but there's only so much you can talk in Cisco Live. This year, we did not cover this topic about the storage metrics, number 3 that you see here. Right, so it's extremely important for those of you who want to understand this. It's best not to multitask, right? And also ask the questions, because you may not remember, but at least you will remember that you asked the question and it was discussed, so you can always go back to the recording and refer it. Right, so this is our focus today, which is storage metrics, and all the crazy little detail that you have been asking questions, but and I've been delaying those questions, saying that no, let's wait by the time we reach there. Okay, so let's start from the very basics of fiber channel protocol. This should not be any surprise to anyone. Essentially, we have different layers in fiber channel, and at FC4 layer, we provide a mapping to the upper layer protocol. Right, this is where SCSI or NVMe has a role to play. Essentially, based on the upper layer protocol, we map it to the lower layer constructs in fiber channel. And what are these constructs? We'll talk next. Also, I think one of the points that you have been seeing, right, as a side note, that SCSI and NVMe can coexist. They can coexist because they are two different upper layer protocols, and none of the lower layers are changing in fiber channel, right? And we'll look at some packet traces and look at those header fields to understand what frames are different and what frames are common between SCSI and NVMe. Okay, so standard definitions, frames, we all know what are frames and sequences. These are ordered sets, or essentially a group of frames which are going in the same direction. Exchanges essentially, when we look at SCSI or NVMe, an IO transaction is mapped to an exchange. So if I'm saying I want to read the data, so I'm going to initiate a read command, and that read command becomes a construct. It becomes a exchange when it comes to fiber channel layers, right? Then we have the information units. So the upper layer protocol are mapped to fiber channel information units. We already talked about the upper layer protocols, and then there are lower layer protocols like bit synchronization, transmission words, fabric logins, and things like that. I'll just keep it here for the sake of completeness, but that's not our focus, right? We'll keep on focusing on the overall traffic and the exchanges. Also, you probably have seen a different version of this particular diagram here. It has been around since I've been around, like much longer than that. As I said, there are frames, sequences, and exchanges, and then a group of frames mapped to an information unit. All right, and this is our header, fiber channel header. Again, should not be any surprise to anyone. It's around 2K bytes. The whole frame length is around 2K bytes. And then you have different fields here. Look at the SID, which is the source FCID of the frame here, right? ID is essentially its FCID. And then DID is also the destination FCID, right? These are generally the things that of a typical switch monitors or not even monitors. It just looks up these things and send it on an egress port, right? And nothing much beyond is very relevant unless we are looking at some additional features like QoS or things like that. The other things that we're going to cover next, but watch out for the OX ID here. OX is essentially an exchange ID. For those of us who have been doing these things, we know what OX is, but sometimes it's not very obvious that OX is exchange and ID is a number. And then you see the sequence count also, right? We're going to look at these things. All right, so how exactly a read operation works in fiber channel is an initiator when it wants to read the data from a storage array. It initiates a read command IU, a command information unit. If you look at the specs, that's the term. Generally, we just call it as command frame because, yeah, I mean, we don't want to overcomplicate it, right? So you'll see that, hey, there's a command frame going. And essentially what they really mean by that is that the command IU is getting within a fiber channel frame, and that's getting passed through the fabric. Okay, so when this command, I'm just going to use the word command frame for the simplicity. When the command frame hits the MDS switch, on which we have enabled analytics. It can be an ingress port or egress port based on where you have enabled analytics. We start a clock, kind of like think about this, that we start maintaining a state of this exchange. But we don't touch the frame, right? So it's going in its original destination. It reaches the target, and the target takes a while to find where the data is, whatever the logic of that storage array is, and it sends the data, right? And depending on how large the read command size is, there would be so many frames, right? Because a single frame, the maximum frame size in fiber channel is around 2K. We just looked at that. So let's say the read IO size is 64K. So roughly translates to 32 frames, maybe 33 frames, right? But something like that, or rough calculation. When the first response is sent by the target, we tap into that response also, and that is what we call as data access latency. In the industry, you probably have heard other terms. I think command to first IO is the other term, right? Because essentially it's the difference between the command frame and the first IO or the response that's coming back from the target. So that's another term that people use. But in Cisco products or Cisco terminology, we call it as data access latency, which is essentially is the time taken by a storage array to send back the first response. And as I said, there may be more data frames that may be going in the other direction. And finally, when all the data is sent back to the initiator, the target sends a response information unit or a response frame. Right? You probably have heard people saying that status is sent over. Status is not the name of a frame. It's not the name of a header, right? We'll look into what exactly status is, right? Just to be clear. When the response is sent, we tap into the response frame also, and then we calculate the time difference between the command and the response, and that is called as an exchange completion time. You probably have heard these terms a lot of times from us. ECT, that's what we say it all the time. Essentially, it's IO completion time or just completion time. If you look at some of these storage vendors, they just call it as latency. And by the way, latency is a very generic word. If you think, what is latency? Like me driving from home to work, it's my latency. I mean, I don't drive to work anymore, but nobody's driving. But it's a very general construct, right? So that's why it's important when people say, hey, this is my latency, it's important, hey, what exactly do you mean by latency? Because later we'll divide these metrics into different categories also. So it's important to understand, are you talking about the time between the command and the data frame, which is what we call as data access latency or DAL, or is it the total time? Okay, I think one point that I want to mention here for the sake of completeness, and that thought just came to my mind. Give me a second. I want to pull a older slide, or like a not really an older slide, but I would say the previous version of these slides that we have been using. And then over the years, what happens is when some people look at the same things very differently, and it was conveying a wrong meaning. So this is from Cisco Live, and if you have this version of the slide, you may want to purge it. And here is the version of that slide. Actually, let me not go to full screen mode. You see the difference here, this slide and this slide? It's taking a while, yeah. So this is the version that I just presented as part of this training, right? Where you have these blue arrows, 2 clock symbols in the middle of the whole transaction. And then this is the version that's coming from Cisco Live with the Cisco Live logo at the bottom of the screen. What do you see as a difference here? The same concept, but anybody?
Different shapes. Different shapes in the middle.
Yeah.
So you those arrows are missing.
Yeah, the main difference is that in this slide, the data access latency seems measured on the target,
You see that?
It's not.
Yeah. Now, when we built the slide in the very beginning, we just kept the things there because we found some free space. It's a matter of real estate space on this slide. We didn't really mean that data access latency is only calculated on a target or ECT is only calculated on an initiator. No, we didn't mean that. But this slide somehow conveys that meaning. Not to everyone, but few users got into that thinking that, oh, I thought you never calculate DAL on an initiator. I'm like, oh, why do you think so? Right. So that's why I suggest if you're still using this version of the slide, retire it. I feel this is a bit better. Now, we are open for suggestion. If you think that no, it still doesn't convey, we can always improve these things. But I thought I'll mention because the previous version was creating some kind of confusion, at least with some folks. Right. So be aware, doesn't matter the location as long as you're picking and choosing the same reference frame to measure these metrics, it's okay. It can be anywhere, just stick to that point, right? Later, when we go in deployment, we'll see that you can do it host ports, or you can measure these on storage ports, depending on how large your fabric is. Your reference frame may change. And what I'm trying to say is that don't change your reference frame all the time. Just stick to, let's say, host port and just stick there, right? And after that, things would be okay. All right, so let's see how.
Paresh, sorry. On this slide, just to be picky, there are two clocks, and it looks like the clock on the exit toward the target is used for data access latency, whereas the other clock is used for host size exchange completion time, which I don't believe is really accurate.
Yeah, that's right. It's not conveying that. So as I said, let's say on this switch, I use a host port, the port that's connected to the initiator, and I enable analytics there. So actually, both the metrics will be calculated right there.
Yeah. So maybe you should only have a single clock rather than two.
Okay, so this is exactly how your read operation works. Now we're going to go one level deep, and we're going to start looking at what exactly flows on the wire, right? So this is a trace taken from a Finisar kind of device. I think it was a JDSU inline traffic analyzer that I use. This is not what you see on Cisco SAN Analytics, just to be clear. Even though we are talking about SAN Analytics, this is not what we see in SAN Analytics. This is what we talked yesterday, that providing packet traces is not the intention of this whole offering. So if you look at these traces, you see that in the very top here, this is a read command flowing, and then after that there are two data frames, right? And then finally the status is good. By the way, I just mentioned there's nothing like a status frame, right? It's just telling you the summary. Remember, it's the summary. And here we have the detailed version of the 4 type of frame headers, right? And we'll go in detail of that, but essentially we have a command frame, then we have 2 data frames, and then we have a response frame flowing. Okay, so let's drill down further. And the whole reason of walking through is to realize that where exactly the metrics are collected, right? And by the way, we are going to look into every puzzle individually, and then in the very big end, we are going to bring all this together, right? So don't get lost and don't think, hey, why I'm looking at a frame, because yeah, there is a reason that we are looking at it. Okay, so if you look at how exactly we construct an exchange, we construct an exchange based on the same exchange ID. So if you look at this example, it's the same exchange ID of in hex 090D, right? The command frame, the 2 data frames, and the response frame are carrying the same exchange ID. That's what makes an IO, or that's what makes an exchange. Next, essentially, if we look in this exchange, then how many sequences are there? Essentially, we are looking at 3 sequences. The command frame has a sequence ID of 06, that's in hex. Then the data frames have sequence IDs of 7B and 7B. Both the sequence IDs are same, and when the sequence IDs are same, we start using the sequence count. So if you look at 0 and 01, Those are the two sequences of the same sequence. Then they are going in the same direction. They are going from the target to the initiator. And finally, when the response is sent, it's a different sequence. Even though it's going in the same direction, it's a different sequence. So we upgrade the sequence ID number. So overall, if you look at this whole transaction, we have one exchange, we have 3 sequences, and then we have 4 frames. Okay, and then we have the source IDs, the source FCID, and the destination FCID. It does not depend on the IO direction. It depends on the direction of the frame, because the IOs are always initiated by an initiator, right? But only the command frame is used to initiate. The data frame is not, and the response frame is not, right? So that's why don't get confused in the direction of the IO versus the direction of the frame. Okay, so we already talked about the exchange ID, but there's something called as the type in the header, right? So every exchange, a different exchange may carry a different type. Imagine if you're running FCP or SCSI along with NVMe, it's possible some of the frames, not all the frames, just some of the frames may have a different type. And that different type is actually told by the type field in the header. So here 08 in hex actually signifies the next layer or the upper layer protocol. And there's a minor detail to that will go in few minutes when it comes to NVMe. But essentially, this is what signifies the upper layer protocol. And by the way, when a switch switches the frame from one port to another, it doesn't need to look beyond the fiber channel header, right? So if you look here, this is where our fiber channel header ends, right? Anything below is like the upper layer protocol, right? This is like specific to FCP, and then we go in a specific SCSI header right here. So a typical switching function doesn't need to look beyond a fiber channel header. But for analytics, once we know that the type is whatever, if we want to detect what kind of transaction it is it a read or a write, that information is only available deep within the header. So if you go beyond, there's a type of read command, and this is where we have a SCSI command field with the value of hex 28. That's what tells us it's a read command. And by the way, there's a long list of kind of read commands in SCSI protocol stack. There's like, yeah, you can, if you're interested, just Google it out. And there's like kind of 20 type of read commands you can make in SCSI. Not all of them may be used by the initiator or the target. That's I would say, dependent on their implementation. But we detect somehow, right, all of them. And once we detect the kind of read command, after that, how do we correlate the data frame and the response frame is using the OXID, right? So after that, we don't really have to depend on like what kind of transaction this is, because based on the command, we know it's a read command. And then we use the OXID to figure out it's actually the returning frames are belonging to the read transaction. Okay, what makes our flow? The initiator, target, and the LUN flow. Essentially, we already know the initiator ID and the destination ID based on the fiber channel header. In this example, it's 02 right here. This is the destination ID. That means this is the target port. And then this is the initiator port right here. 020105 is the initiator. 020062 is the target. And then we don't carry LUN value in the fiber channel header. So for that, the analytics function must be enabled so that we can do a deep packet inspection. And you see that the LUN value here is 14, right? So this is what makes our ITL flow. Okay, there are more fields. The LBA, which is the logical block address. So essentially, we're just, the initiator is trying to say, read the data from this location, and then read this much data, which is the transfer length here. It's a 00, I mean, in hex, it's 8. But we don't use this number. We don't use the transfer length. I think I'm talking next in the next slide. I'll explain that. This value is carried in the header, but we don't use the transfer length to calculate the IO size, just to be clear, you know. So, okay, talking about the good SCSI status that, you know, we keep on using all the time. See that SCSI status is actually a field in the header. It's not the name of a frame, right? And the SCSI status that you see, there's a long list of, I would say, error codes that can go in the SCSI status. And one of the error codes is a good status, which is not really error, but yeah, it can be a code, right? So that's what we call. Now, this status could be a long list of other things and some of the metrics that we calculate, right? But this is exactly where the status is returned. Let's say something goes wrong. Let's say the target cannot read all the data. So it's going to take a while. And then if it cannot finish the whole IO, it's going to send back some kind of response based on what the error is. And until the response frame is received, this is what we call that the exchange is still open or it's still active, and it correlates to the outstanding IO metric that we have. All right, how do we calculate the ECT? Now, notice that some of the metrics are actually sitting within the header. So we just go and pick the value from the header, right? Like if you want to know what is the type of transaction, so I can go and look in the header, which is 0x28, hex 28, and that tells me it's a read transaction, or that tells me I can look at, let's say, the transfer length to figure out how long, what is the IO size, even though in SAN analytics architecture, we don't do that, but still it's possible. However, the ECT is not carrying within the header. What we generally do is we maintain the states and we take a time difference between the command and the response, right? So this is where our clock thing comes in play, and based on the same exchange, when it goes in the other direction, we take a time difference. Similarly, DAL is not carried in the header. We take a time difference between the command frame and the first data frame, which are belonging to the same exchange flowing in opposite directions.
Paresh, one question. It can be a very minor detail, but just to understand, commands are coming from hosts and responses are coming from targets. So when you say compute the difference between the time of command and the time of first data, I believe the time of command frame is taken on the ingress port into the switch toward the host. But the time of first data is maybe taken on the storage port, the one facing the storage. So in between, you have the latency of the switch. So I would like to understand, do we take the time on the same side of the switch or not?
So to answer your question in short, we'll go in detail of that for in a few minutes by the end of today's session. But generally, we recommend that you enable analytics only on one port. Don't double inspect the traffic, right? So if you have one switch, and if I go back to the original drawing that we had, right? So let's say we have one switch between our initiator and target, and there's one flow. For the sake of example, there's just one flow flowing. So you have this host port, and then you have the target port, right? Don't inspect the traffic twice. Don't do that. It's not required, and we'll cover that into a lot of detail. This is a FAQ that requires a lot of explanation, right? So you pick and choose. Now, if you select host port here, when the command hits this host port here, there's an NPU behind it, right? So let's say we have a NPU, and NPU, let's make NPU in orange color. So the command frame reaches this NPU, and when the response or the first data, whatever metric you want to calculate, from the same port reaches the NPU, this is where we take the time difference.
Okay, so on the same side of the switch. Okay, thanks.
Yes. Now, for the sake of theory, what we can do, like probably I can show you that, I mean, just for the sake of understanding, what we can do is enable analytics on both ports and see what happens, right? There would be a time difference, yes, right? There's no denying to that. Obviously, there is like the switching latency, so the metrics calculated at different places in the fabric will differ, but the difference is irrelevant, and we'll cover more details on that. So uh, hold that question if you, or hold that thought if you're thinking, hey, why it's irrelevant. But uh, if you deployed the way we recommend, is that enable analytics only on one port, or enable or inspect your traffic only once in the end-to-end data path. In that case, your command and the response or the data frames will end up hitting the same NPU, and your times would be as accurate as up to nanoseconds or microseconds, whatever time it takes to finish the exchange. This is where we were. So essentially the point is that the data access latency is not available within the header. You can't just go and read it. It's actually the difference of the time when the NPU sees the command frame and when the NPU sees the first data frame belonging to the same exchange of the same type in opposite directions. The standard checking that we should be doing to make sure that actually it belongs to the same transaction or exchange. Okay, and this is about the IO size. Now, IO size actually is carried in the read SCSI header. You see the transfer length, and that transfer length is not going to make sense because in hex it's 8, right? So what is 8, by the way? Who wants to take a guess? Anyone? Now the block size, it depends on the block size, by the way, right? And then block size you can define if you, I mean, when we format our hard disk on the laptop, right? It tells you that block size and everything, right? Which we never care to change. It's like that, right? So it's the number of blocks. The 8 number is the number of blocks. It's not the number of bytes. Okay, and the byte size or the size of a block is actually negotiated in the very beginning based on when you're formatting or building your volumes, right? Be it a local disk on a laptop or it's a volume on your storage array. So most of the times, it may change. There's nothing like a standard, but in this example, the block size is 512 bytes. So if I multiply 8 by, so yeah, in decimal in 512. So this comes out to be 4096. And is it matching with the hex value of 1004096? Right, making sense? That actually the FCP data length that you see here, this is where the fiber channel header also carries the amount of data that is being transferred using this command, right? So in the SAN analytics, we don't use the transfer length because it's not in bytes, it's in blocks. And then blocks doesn't make a lot of sense for the folks, right? Like it's not a user understandable concept. And in the very beginning implementation I remember, not sure before FCS or probably in the first release, we were actually doing data length. We are showing 8 transferred and then 8 blocks transferred, and that's not the best thing to do. So we moved over to the FCP data length. Okay, making sense that what is the difference between transfer length and FCP DL? FCP DL is FCP data length. That is in bytes, and transfer length is in blocks. And then the size of a block is negotiated in the very beginning, or may not be negotiated. I'm not sure on that, so don't quote me on that. It really depends on different factors. Yeah, somebody asked me once, when, yeah, so just to be clear that actually it's understood. Okay, number of read, what is IOPS? So again, IOPS is not something that is sitting in the header. You have to calculate the number of transactions completed and then, figure out how many completed within a second. Okay. Now we'll cover into detail of that how exactly we calculate, because we have two kind of metrics in the NPU. And here's a question. I want to float this question with you guys. That let's say the NPU, if you look at the NPU granularity in microsecond level with millions of IOPS flowing, there could be two scenarios. One scenario is when the NPU sees the command frame, but the IOs may not finish, right? Let's say the storage array is overloaded. It's denying all the IOs and it's saying, I'm not going to send any more data and I'm not going to send back any more response. So the NPU will keep on counting the command frames. So that's one way of calculating IOPS. And if the NPU is seeing 500 command frames every second, it's going to say IOPS is 500. The other scenario is actually it sees the response frame also, and that would signify that these many exchanges or these many IOs got completed within a second. So you see that the difference between the IOs which were initiated versus the IOs which were completed. Okay, this point, like the number of IOs initiated versus the number of IOs completed, it's a very important point. You'll see two different metrics in the NPU, right? And then it also relates to a timeout metric that I'll talk in few minutes. But remember, when somebody says IOPS, and even without the whole under the umbrella of SAN analytics, in general, when somebody says IOPS, these are small little details that we should be looking. What do you mean by IOPS? Is it the number of IOs which were initiated, or is it the number of IOPS which were completed? Right. And by the way, it really depends on where you measure, because if the storage array says that I completed 500 IOs, that may not be the reality of the host if we end up dropping the frame in between anywhere. It can be a SAN or it can be anywhere within the host stack. Right. Let's say the HB drops, let's say somewhere within the host stack, we drop it. So if the drop happens, let's say the target reports or the storage array reports 500 IOPS and the host may report 400 IOPS. Those kind of things are possible, just to be clear. Okay, what is outstanding IO?
Question. Is that where we can determine the outstanding number of IOPS and perhaps recommend queue depths?
That's exactly the next thing.
Okay.
Okay, and what is outstanding IO? Essentially, this is the number of transactions that are yet to be completed, right? So when the command frame is observed, but we probably haven't observed the data frame, or at least not response frame. Maybe data frames are observed, but if the response has not been observed, then the exchange is still open, right? So we'll go into the metrics. Like these are, the generic metrics like IOPS or throughput or ECT and DL. They are like higher level constructs. This is not exactly what translates to our NPU metrics, right? So I'll talk about next that actually outstanding IO. We don't have an outstanding IO metric in the NPU. If you do the show command, you won't see this. You will see an active IO metric, right? So we'll talk about that next. But remember, what we call it as outstanding IO is essentially, these exchanges are still open. They haven't really finished. And how do we define being finished is when we receive a response frame with a good status. Okay, talking about write operations, similar to the read operation, but then there are some additional steps here, right? The initiator.
Paresh, can I just ask a quick question, please? So you showed some packet size of various read and write transfers. So when you look at this, the line of business application that's running, going back to my benchmark yesterday of questioning, so you take a benchmark of a specific line of business application. They may be performing different read, and that the read and write transfer of data may be unique to that line of business application, and it provides a latency number. You go to another line of business application and they're using a larger read, write, transfer. That's not determined for a customer who is trying to get exchange completion time for these unique line of business applications. Do we offer anything that says, okay, here's your latency time or your exchange completion times with this data transfer? Here's the exchange completion time with this data transfer size. Is there anything in the metric? Is that even a valid question, for one? I'm just wondering if I'm overthinking this.
I think that's a very valid question. In fact, I know the Virtual Wisdom product does it like that. You know, they categorize the IOs in different IO sizes and report the time differently. We also have a similar concept. I'll talk about that later today, a normalized version of the metrics. And the idea is very similar to what you said.
Okay, and then one final question for the moment. You're showing a target here. A lot of our customers have vPlex. Can I replace the target verbiage with a vPlex? And how do I know what the physical device is doing on the back end of the vPlex? Or do I just calculate from the vPlex target to the initiator? Is that what I'm looking at, even if it's a vPlex environment?
Yeah, so I think we'll talk about that in detail when we talk about deployment, but essentially devices like vPlex and SVC, they are virtualization device. Essentially, they act both as an initiator and a target. Right, so
yeah, and I'm just wondering how I'll defer, wait till you get to there, but I'm just wondering if there's, how that calculation is put together, because the actual back-end physical disk is actually connected to the vPlex as well. So I can wait for that. Thank you.
Yeah, and we are, as you can see, right, we are at very lower level of this whole puzzle, and then slowly we'll have bigger pieces, and then at the very end, we'll bring all of them together. Right, so that's where it will start making sense, yeah.
Okay.
Okay, so write operations, this time we have a command frame, but the type of the command frame is different. This is a write command. The concept is same. Yeah, we don't have 2 clocks or 1 clock, whatever helps you to understand it better. But when this command or the write command reaches the target takes a while. And what it's doing, by the way, it's trying to allocate some resources, because the initiator is saying, hey, I want to write 64K of data. Are you ready? Right, so essentially that's what it's doing. It's getting ready, and it takes a while. It sends back a transfer ready. Okay, so this is an additional step in the write transactions. So the time difference between the command and the transfer ready in write transaction is called as DAL. After that, the initiator sends back the number of frames which can accommodate this whole data that needs to be written to the target. And the transaction gets finished using a response frame. The time difference between the command and the response is what we call as ECT. Now, there's some small little details here which may or may not be relevant, but I'll just say for the sake of completeness. First of all, the initiator may request a large IO size. Let's say the initiator here requests 128K of data to be written to the target, but the target may not agree to that. The target may say, I just want to receive 64K because that's all I can do. And it's really vendor dependent, architecture dependent. This is not a generic concept, or it may be a generic concept, right? So because we don't really know, when you enable the solution, you don't really know what storage is and different vendors, architectures. This goes back to this problem statement that we were talking yesterday in the very beginning, right? So bring that logic here, or that whole notion of different architectures here, it's possible that the requested write IO size is 128K, but the target may only agree for 64K. So the data will be sent, like 32 frames will be sent here. And then after that, there would be another transfer ready flowing, right? If this transaction has to get completed, because the target has to acknowledge that it can receive more frames, right? So remember, it's not true that there will be only one single transfer ready in a single write transaction. There could be more than one. Okay, so that's one. That's one point. The second point is that even though today, as of today, we are only calculating the DAL, which is the time difference between the command frame and the transfer ready, you could say that, if there are multiple transfer readies involved, we should be having multiple DALs, right? That's possible too. So that's something we don't do today. Okay, but those things are possible and it has come up at times. The next point is that when the host or the initiator receives the transfer ready, it may not send the data immediately. And I'm talking about this delay here, right? By theory, this is called as host delay. We don't calculate this today. We will do this in the future, right? And this is going to be very important because we know the total time taken to finish the transaction. Let's say ECT here is 500 microsecond and DAL is 100 microsecond. And we are thinking, hey, DL is super fast. Where are the 400 microseconds going? It's possible your host delay is 300 microsecond because the initiator receives the transfer ready and just sitting with it. It's just too busy doing other stuff. Or there's something else going on. But we don't know that today. So we figure that out indirectly, right? What we generally do is that if DL is lower and the ECT is kind of higher, we kind of take a guess that it may be the host trying to delay. And by the way, that guess has been proven. I'll not sure if you guys remember, I've talked about that European customer case study, those graphs flowing every 10 minutes, with a kind of heartbeat kind of graph. This is exactly what happened there. We did not know, we did not have the host delay metric, but actually we took a guess that, what, the DL is lower, then where else can the delay? Maybe it's host. And that's how we walked in that direction, even though we don't have the host delay being calculated today. But we'll do that in the future. Okay, any questions on that? Because it's not, I don't have slides on that. So if you have any questions, this is the best time to ask. Small little details, by the way, and you get into trouble, just call TAC. I mean, that's the standard thing.
If the target only wants to receive 64 and not the full 128, how do we know that? It would initiate more than one transfer ready, but is it the number of blocks, the transaction size? I mean, is there some way to determine whether we're going to have a requirement for more than one transfer ready from the target?
The number of transfer readies per IO exchange is something we want to do in the future. So we don't tell that today. So that's one thing. There would be some other metrics. Now, it depends on it really depends on why it's not finishing the transaction. Let's say there is a reservation not reservation conflict. Let's say there's a queue full. So actually we have a metric for queue full. Or let's say there is outstanding IOs, the queues are getting full and it's not really that full that it responds back with a queue full condition, because that's something you are hitting your threshold of 100%. But problems may happen at 95% too. So at that time, your active IO count or the outstanding IO count would be way too high. So those are indirect signals. those are some of my guesses, but it really depends on what errors. And by the way, if it goes way too beyond, SAN analytics may not be able to detect it, right? Because as I said, this is not exactly the use case, pinpoint every packet trace, every other error, those kind of things are possible too. So at that point of time, it is best that we enable the host side debugs or storage side debugs, or even if those guys, so generally what would happen is these guys will not agree, right? And they say, no, I'm doing fine. And then SAN analytics will say, okay, guys, this is way too beyond our capability. And that's the use case for an inline traffic analyzer to figure out, all right, let's see what exactly is going on. So there's no simple answer to that question. I mean, yeah.
I guess what I was asking is there a deterministic way to know what a particular target type will accept from an IO write request without having to span it into more than one transfer ready?
No. I would say that's really target dependent. There's no single answer for that. Different vendors, architectures, all of them may end up doing different things.
Okay.
And I guess it's also a function of how busy that device is, because it needs to allocate those buffers, right? It's not going to directly write to the backend media. So it needs to hold this thing in, like, whatever you call, sometimes like what those, those things that make the write command faster, like some kind of, in memory, and like, yeah, all these guys have different architectures to make these things really fast. So it's really vendor dependent. Okay, so essentially I have packet traces for write command too. I will not go in detail. We have covered most of these things, but you are welcome to take a look on these things. And if you have any questions, ask them later. Okay, going to the NVMe, the way read and write operations work over NVMe, the good news is they work exactly the same. Just the name of the IUs are different, right? Or the information unit is different. You see now it's called NVMe command IU, but the whole concept is same, right? The way we calculate DAL and ECT. Okay, the frame transactions, different directions, exchange IDs, sequence IDs, and everything remains the same. The whole concept is same. The packet headers would look different, not the fiber channel header, but because the NVMe is a new protocol. And some of the points that I want to highlight, again, not everything. I think this is one interesting point, may not be relevant, but something very interesting to know. That if, not sure if you remember, when we're looking at the type header right here, it's actually 08 hex. It's the same thing that we saw in the SCSI read command also. And here, this is actually a packet trace of a NVMe read command. It's still we see 08x, right? This may be a point of confusion, but it should not. This is exactly by design. This is the reason that we are able to support NVMe and SCSI in parallel on the same fabric without any change, because we did not change the type. Okay, now this is a data frame. That's why you see that value same. However, when there are control traffic flowing, something called link service request and responses, that is when we used a hex value of 28. And that's what indicates an NVMe transactions. Not transactions, you will not detect that without really going, but actually it's a FC4 type concept when the devices do login in the fabric. When you do show FC in its database, that's when it shows. But in the data frames, you'll not see that if you're just looking at the fiber channel header. And that's totally by design. Okay, we detect only when we enable SAN analytics, and we start inspecting the frame headers after that. And obviously after that, you see that there's a differentiator type and there's a whole new header. That's one interesting piece. The other interesting piece is that there's nothing like a LAN concept in NVMe, right? There's a namespace concept. And just like you have a LAN ID, or LAN by definition is an ID, right? Logical unit number. Yeah, it's a number. So here, the equivalent of that is a namespace ID. And you see the value here, which is hex 2D. Right, and just like we use the data length field, we don't use the number of logical blocks, right? So that field remains unchanged. You see the LBA, the logical block address, and the number of blocks. We don't use that, even though that's get carried in the NVMe header. Okay. And by the way, the format of the response frame is same between the SCSI and NVMe. So don't get confused. When you see a response frame of an NVMe transaction and you see SCSI status there, right? That doesn't make sense. Actually, that's by design, right? There would be a SCSI status flowing in an NVMe transaction. That's very interesting, but it's by design. Okay, write operation, very similar to the way SCSI works, all those different points that I just mentioned. So nothing to repeat here. You have the packet headers. You can take a look on them whenever you got nothing better to do. Anything interesting here? No, I think all the interesting points we already talked about. Okay, these are side facts.
Sorry, can you back up one slide? I just on the first link.
This one?
No, it was the packet capture, the one more forward, I believe. It was the very last slide. We just
the read one or the write one?
It was the NVMe one that looked like this.
This is for NVMe reads.
Yeah, not this one. The next one, I guess, the one that showed.
This one?
Yeah. So when the transfer ready, there's a burst link, but I don't know what that is. You have it highlighted in some of the animations on the slide.
Yeah, we're going there next.
Oh, okay.
Yeah. Now, this is supposedly a concept of a first burst is actually, if you look at the standard, it's only written in NVMe standards. But actually, the HBA vendors, at least I know Emilex, has implemented it with SCSI too. So even the existing non-NVMe enabled HBAs are able to do first burst. And what exactly first burst does, that it eliminates that whole extra step of transfer readies, right? Why do we need transfer ready? Because we want to make sure the target is ready to receive that incoming data. So what happens is in the very beginning of the, when there's a ploggy happening between the initiator and target, and there's a process login happening, all those logins that happen, at that time, they actually negotiate that target. You always make sure that you reserve this much buffers for me because I can send this much data to you anytime. Right, so they agree on that. Let's say they can agree that the target, you always make sure that you allocate 64K of buffers for me because that's what I can send you without even telling you, right? So allocate that room for me, right? And once they negotiate on that value, what happens is that if the initiator wants to send, it doesn't do that, or it doesn't really wait for the transfer ready. The target may still send back transfer ready, but it's not going to wait and just sends the data, right? So that, if you look at this, and you remove this whole optional step here, it becomes a single step transaction for read, even for write commands. The other optimization is, which I don't have a drawing, but it's a merged response of in the read transactions. If you go and look at the read transactions, you notice this, right? Like we are sending a different frame for the response. If there's space available in the last data frame, we could have actually merged these two things into a single frame and send it over, right? So that's another kind of optimization that has been, the HBA vendors are doing. Okay,
so Paresh, would you say it's a true statement that NVMe traffic? I've been told this by EMC. I'm not sure if it's accurate or not, that there's 12 less instructions versus SCSI writes. Is that an accurate statement? And are you showing that to be true on your slide here?
I'm not showing that on the slide, but in general, that statement is true. Last time I checked, there were 3 mandatory transactions, and there were a couple of more optional. So I think that's where it goes to number 12. In SCSI, if you just look up SCSI spec on Google, there are like 300 type of commands out there there are 20 different kind of read commands out there. I think that's a legacy reason, but overall, the idea is same.
Okay, thank you.
Yeah, but I mean, here we are not.
Example,
Say that again.
sorry, in this example where we don't necessarily have a transfer ready before the host starts sending, the initiator starts sending its data, how do we calculate the data access latency?
Well, yeah, I totally love that you thought about that, because look at my third bullet here. We don't do that today.
Okay.
Right. Yeah. But we handle these kind of optimizations to calculate other metrics like ECT and things like that. We don't do DAL with host burst. Right. So these are some of the caveats, or like, things you may hit in the future in some kind of scenario. Hey, I see accurate value here. I don't see it there. And then, oh, is it doing host burst? Oh, yes, I see that. All right. So we don't do that today. Maybe next release we'll have that working.